Hello, and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This is part one of the video on Newton's laws and resolving forces, and in this video I'll just be going through an example of everyone's favourite, the lift problem. Okay, so here we have a child travels in a lift. The mass of the child is 32 kilograms and the mass of the lift is 468 kilograms. The lift is descending at a constant deceleration of 1.5 metres per second squared. By modelling the cable that supports the lift as being light and inextensible, find the tension in the cable and the magnitude of the force exerted on the child by the floor of the lift. Right, so key information then. We've got a child of mass 32 kilograms and we've got a lift of mass 468 kilograms. It is descending, so it's moving downwards, and it is a constant deceleration of 1.5 metres per second. Right, so let's begin by drawing a really good diagram. So, first of all, we've got the lift, and then we have the child in the lift. And then we just need to think about what forces are acting on this system. Well, we have the weight of the child, which is going to be 32g, g being acceleration due to gravity. And we are also going to have a force downwards of 468g, which is the weight of the lift itself. We have the lift being supported by a cable, and in that cable there is a tension force which we'll label T because we don't know the value of that tension force at this point. What we also have is that the lift is descending, so I'm going to draw a direction of motion arrow here to the side of the diagram. It's descending but at a constant deceleration, so it's descending while slowing down, which means that my value of A for the acceleration of the system is going to be negative 1.5. That's very important. It's descending, but the acceleration is negative because the system is slowing down. So, what I'm going to do is I'm going to form an equation and resolve to find the tension in the cable. So, what I like to do here is I like to resolve in the direction of motion. So I'm going to make my positive direction downwards because that is the direction in which the lift is moving. Okay. So I'm going to say that my resultant force is equal to mass times acceleration, and my resultant force is that any forces moving in the direction of motion minus any forces that are opposing the motion. So in the direction of motion, I have 32g, which is the weight of the girl, plus 468g, which is the weight of the lift, and that's being resisted by a tension force which is acting in the opposite direction. Now that's going to be equal to the mass, now that's the total mass of the system, so the 32 and the 468, so that's 500, multiplied by the acceleration, which is negative 1.5. So, what I have here, I have 500g minus t is equal to 500 lots of negative 1.5, so that's negative 750. So, rearranging that, I can see that the tension is going to be 500g plus 750. Now, in A-level mechanics in maths, we take g to be 9.8, so that's going to be 500 lots of 9.8 plus 750, which means that the tension in my cable, 5650 I think, 500 times 9.8 plus 750, 5650, lovely, 5,650 newtons. So that is the magnitude of the tension in the cable as we've been asked for in part A. Okay, let's have a look at part B. Part B is saying the magnitude of the force exerted on the child by the floor of the lift Now, for this question here, we need to think about the forces that are actually acting on the child. So to do that, I'm actually going to draw a new diagram with just the floor of the lift and just the child. Now, the forces acting on the child. The forces acting on the child are its weight, which is a force of 32G. And there is a force being exerted on the child by the floor of the lift. Because what I often ask students to consider is, what is it that's causing the child to move? And they say, it's the cable. It's not the cable. What is causing the child to move is the force from the floor of the lift pushing the child upwards. And that is the force that we're going to consider in the second part of this question. And I'm just going to draw it like so. And I'm going to label it R because we consider it as being like a reaction force from the floor of the lift on the child. Now, the system is still descending with the deceleration of 1.5, so it's still A equals negative 1.5, descending but slowing down. And then I just need to do similar to what I did in part A, resolve in the direction of motion using resultant force equals mass times acceleration. So in the direction of motion, I have 32G. Opposing the motion, I have this force I've called R, which is the force of the floor of the lift on the girl. And that is going to equal the mass. Now that's just the mass of the child because we're resolving forces for the child, multiplied by the acceleration, which again is negative 1.5. So 32G, let's work that out as a number. 32 times 9.8 is 313.6 minus R is 32 times minus 1.5, which is minus 48. And rearranging that, I'm going to get that R is 313.6 plus 48, which is 361.6 newtons. Now let's just consider this for a moment. The force, the weight of the girl acting downwards is 313.6, and the reaction force from the floor is 361.6. It's greater. And that makes sense because the force going up must be greater than the force going down to cause the lift to slow down. And what this is actually an explanation for the feeling that you have if you're in a lift and you're going down, but the lift starts to slow as you're reaching the floor you want to get off at. As that lift is slowing down, you can actually feel as though you're moving upwards. And that's because the force exerted from the floor of the lift is greater than your weight. And that's what's happening here in part B. Okay, join me in the next video where I'll look at a scale pan with two masses, one on top of the other. I'll see you then.